Dude, you're making like, what does that say? $200 a minute.
You can use 0 and 1 instead of A and A bar. I saw your designation there. But in general, you want to, your inputs to the system are supposed to be 0 and 1, so I would just put those in the input table. I didn't take off points for that, but just for future reference. Is Y up here?
That's me.
That's you. That was your homework too.
I didn't care what thanks.
Okay.
Oh, this is that old one. This is the, okay.
Yeah, the K-map.
That's homework too.
Okay.
I missed the lecture on K-maps, which is YA.
Okay.
But that's okay.
Do you understand them now?
Please tell me you do that.
Okay.
I don't recall. I have
Mine is fine.
Your brain is okay.
All right. So you people rock. Awesome job on homework 3. I was really happy with what everybody did. I think you pretty much got the concepts down that I wanted you to get. Some of those questions were designed to teach you things, okay, not just to test what I had explained up here, but to actually get some new concepts from doing the exercises, and you were able to do those, which is really good. So good job on that. If you turned your homework in on paper, it's up here. If you turned it in online, then I gave comments to you in the Dropbox. And in either case, your grades are available on the grades part of Angel. Okay. So I didn't put those in the comments, but if you turned it in paper and I had any comments, I put those comments directly on the paper. So a few general comments on homework, first of all. So I've been pretty generous so far about late homeworks. Going forward, I'm going to have to cut down on that a little bit. So when a homework is due, it's going to be due at 2:50 on the day it's due. And I'm going to start being more of a stickler for that. So if you warn me ahead of time that you're not going to be able to have it done by then, that's fine. We can make some other arrangements. Otherwise, I'm going to start taking off 25% per day that it's late. So after 3 days, you'll basically be down to 0. So, and that's mainly just to make sure that we're in a position where we can go over the homework on the day that I give it back. Okay, just for fairness to everybody. So it'll be important to make sure you get those in on time. Again, submissions, try to stick to PDFs or JPEGs or plain text. One person wasn't able to get their document file converted to a PDF. If you're having trouble with that, ask me about it or find somebody else who's done it and see if they have an idea, or just print it out and turn it in. Yeah?
I like to mention that with Word you can save as PDF.
Okay. Does it save figures and all that stuff successfully, or?
Yeah, I've been turning everything to you as a PDF, and from Word, you just go to Save As and choose File Type.
Okay, good to know. I use OpenOffice, and usually it can read doc files, docx files, but once in a while it doesn't, and I have to actually find a Windows machine and look at the assignments on there. So okay, cool. Like I say, worst case, just print it out and turn it in paper. I got some really cool technology over the weekend. Anybody got one of these?
What is it?
Like totally rocks.
Did you like change the page?
No, even better. Like this, slide it back with the stapler. Turn your stuff in. I'll let you borrow that.
Wow.
Crazy.
Okay, a couple of comments on specific questions. Question 1 was on that funny-looking sequential circuit, and the only thing that people had some confusion about was this state where A and B are both 0, and that was intentional. That was supposed to be a confusing case. I wanted you to think about it. If you're in a state where, say, A is 0 and B is 1, okay, that's fairly easy to analyze. If B is 1, you know the output of this OR gate is a 1. Okay, and so you can immediately say Y is a 1. And if y is a 1, now you know you have a 0 going into this OR gate from the bottom. And you know a is a 0, so you have a 0 here. So you know absolutely you have two zeros being OR, x is going to be a 0. Okay, if you go from there, if you drop b from 1 to a 0, what's going to happen? Well, y was a 1, you had a 0 and a 0 coming in here, x is a 0. Now you have a 0 coming in here, which gets inverted to a 1. That's going into an OR gate, so the output is a 1. The fact that you drop b from 1 to a 0 doesn't change the output of y, because this input here is a 0, it gets inverted to a 1. That's enough to make the output of the OR gate 1. So once you've gotten to a case where y is equal to 1, it's going to stay at 1 even if b drops to 0. Okay, so that's going to remain 1 and that's going to remain 0. Okay, that's the memory part of this circuit. Up here, we were able to set either x or y to be 1 based on a and b. When we drop them both to 0, the input gets latched. Okay? So and when you write this in a truth table, probably the best way to do it is to just write something like x, y. Same as previous values. Okay, something in there to designate to me that the value of x now is whatever the value of x was before you entered this state, and the value of y the same as what the value of y was. Okay, sometimes you'll see these things written you might see that designation sometimes where you put these little subscripts to say the value at when you put in 0, 0, the value of x, whatever the value of x was a moment before. Okay, the n minus first value of x and the y minus first value of x. If you think of these as sort of a sequence of samples of x and y throughout time, the value now at time n is the same as what it was at time n minus 1. You'll see that sometimes in data books. Okay, the point was that it's a memory element. A few people caught the fact, though, that if a and b are both 1 and you change them both at the same time to 0, the circuit will probably oscillate. If you were to start chasing these values around and see what happens, the outputs actually change back and forth between 0 and 1. Okay, if one of these things drops to 0 and the output stabilizes, and then the other one drops, then the circuit acts like a memory. Okay, I wasn't looking for you to catch that oscillation. If you said the output stayed the same as it did before, that was full credit. Question 4, where we're trying to detect these patterns of 0, 1, 1, 0. Okay, I left a lot of variability in that question, and I accepted pretty much any of the following answers. If you gave me a circuit that could take inputs like 0, 0, 0, 0, 1, 1, 0, and at this point it said, I've got a match, that was good. If you had a circuit that said 0, 1, 1, and then you put in a 1, and then you put in a 0, 1, 0, and matches, that's fine. If you put in something that looked for 0, 1, 0, 1, 1, 0, and it said, oh, here's a good pattern that matches, that was fine. Some people made a circuit that would say 0, 1, and when they put in a 0, it said, oh, it didn't match, start over again. And then you'd have to put in a 0, 1, 1, 0 to match, and it would not detect this as a good match, but it would this. Okay, that's another way to do it, and that was also fine. I think those are the main variations. Anyway, as long as you explained to me what you were trying to do, and you built a circuit that did it, I gave you credit for it. Okay? In general, all these are valid ways of detecting patterns, depending on what your application is. If it's a combination lock, you probably don't want to do anything that tells somebody when they got the combination wrong. You don't want them to know that they got the first 2 digits right and the third one was wrong. So, and there's ways you can design it that will or won't do that.
So the better case is the last one for the, or which is the better?
Security wise, you mean? So you don't give away hints?
Yeah.
It's an interesting question. It kind of depends what kind of analysis you're doing. You know, you can actually do things where you can plug something into a power outlet in a wall, and you can monitor fluctuations in the power supply. And while you're doing that, you can start trying to get into a secure router that's hooked up to the same power lines. And if you know the algorithms that are being used, you can look at fluctuations in the power supply and tell where you are in that search algorithm inside that router. And you can sort of sneak up on passwords that way. Okay, fairly theoretical, but there's cases where that actually works. So I would say if inside your circuit you're doing something different as soon as they get the wrong combination, you might be a little more exposed. But that's a whole different area, and there's some really interesting stuff in security and encryption and ways to crack it. And, do you know what Tempest is? Storm Tempest, yeah?
It's something to do with like you look at power fluctuations or something, you can see what's on somebody's monitor.
Yeah,
and it's on the
exactly.
wall.
So we talked in the beginning of this class about when a transistor changes state from 1 to a 0 or from open to closed, or when a wire opens or closes, it changes current flow and that generates an electromagnetic wave, and that can interfere with other things. But you can pick up that electromagnetic radiation, and theoretically, if you know the design of someone's laptop, you can monitor what's coming out of that laptop electromagnetically and tell exactly what's going on inside, possibly to the point of being able to recreate what they're seeing on their display. Okay, and you can do this from like the parking lot outside a building. And so in the 80s, in particular, this became a big concern, largely for the government, and it was called Tempest. And the idea was to come up with ways to shield your electronics. So when I worked for Naval Research Lab, we would do certain things in rooms that were completely enclosed in copper, so it was electromagnetically shielded. And whatever happened in there, none of the radiation would get outside that area. And the idea was people could be, driving by outside the gate, monitoring this stuff and decoding what's going on. So there's all kinds of interesting effects out there. So on question 4, the one thing that some people did that I couldn't give you credit for, so we're trying to detect this pattern 0, 1, 1, 0. So okay, so there's different ways you can do this, but basically you start in this stage, you get a 0, you go over here. You get a 1, you come over here. You get a 1, you come over here. And then if you get a 0, you've found your pattern. If you're in this state and you get a 1, it's important that you go back to the beginning. Okay, if you were to simply come back to this stage, okay, then you'd be detecting patterns like 0, 1, 1, 0, 0, 0, 0, 0, right? 0, 1, 1, and then a bunch of 1s, and then finally a 0. And then at this point, you would go over to your concluding state. And you'd be matching a pattern of 0 followed by 1, 1, followed by any number of 1s, followed by a 0. Okay? It's a different behavior. Now, there may be cases where you want to do this. Okay, that might be something you're looking for when you're parsing a language or something like that, but it's a different result from matching a simple 0, 1, 1, 0. Okay, and so if you did something like that, I gave comments about that. Question 5, people did really well on. I did not need you to generate the clock. Okay, I actually said in there. assume there is a clock that pulses low, high, low whenever an input character changes. Okay, so you didn't need to generate that clock yourself. A few people did, which is fine. You can generate it the way we did in that example in class, where when you press either one of those buttons, A or B, they get ORed together, and that generates a clock. That's fine, but it wasn't required to. But I did need you to use two inputs, A and B. Okay, and there were some people who used a single input. Where if this button is pressed, you're inputting an A, and if it's not pressed, then you're inputting a B. Okay, and I saw some good circuits for implementing that, but there's one problem with that, which is you don't know when you're pressing it and when you're not. If you just press the button, is that a single A or is it multiple A's? Okay, so the idea of having two buttons is nothing happens until you push one button or the other. Okay, if you only have one input, you need to have some kind of rule about when you're going to sample it and see whether it's an A or a B. Okay, so I took off a little bit for that, but if the circuit implemented that kind of approach correctly, then you got credit for it anyway. So you needed to have two inputs. In the actual circuit itself, you did need some combinational logic in there. Okay, so the state machine generally has two pieces. It has this sort of sequential component, which are the flip-flops, and then there's combinational logic. So you write the Boolean equations that say something like S3 equals S2 and button 1. Okay? Well, what that means is when you feed the data input on flip-flop that corresponds to S3, it needs to come from an AND gate. And the input to that AND gate is the state S2 and the state of button 1. Okay, and those need to get ANDed. And in a lot of these, you actually had two or more terms. Okay? And so you're going to need an AND gate and an AND gate, and you're going to need an OR gate to put those together. Okay, and you need to actually write those, that part of the circuit, create a combinational circuit that takes those inputs, generates the output. And then 5D, the last question about positive going edge or negative going edge, I gave credit for any answer you put. Okay, I just wanted to see your ideas on which would be the better approach to use. There's no clear single answer that's definitely best. It depends kind of on the requirements of the problem. Now what I had in mind, I said when you push a button, this clock gets generated and goes high and then low, low, high, low. Presumably, you're going to push that button, you're going to hold it for a fraction of a second, okay? But probably longer than it takes this clock to pulse. If you trigger these flip-flops on the positive edge, as soon as you press that button, it's going to load in whatever value is on the D input for each of those flip-flops. And that value may not get set until the new state of the button has trickled through all of the combinational logic. Okay, so you may have a race condition there. If you set it on the falling edge, there's a better chance that this circuitry will stabilize. You'll have the correct values on the D inputs, and then when the clock drops low, it'll load in a nice stable value. Okay, but there's other reasons that people gave why you might want to use a positive edge as well. So, that had some good answers on it. So those are the main things that I saw. I think pretty much everybody figured out the circuit. I don't know if you got the punchline to it. It's basically a down counter instead of an up counter. So it counts from 7 down to 0 and then back to 7. And it's kind of cool because it's exactly the same circuit as an up counter, except when you want to count up, you use negative edge triggered flip-flops. And that counts from 0 up to 7. And if those are positive edge triggered, it counts from 7 down to 0. But it's that easy to switch the direction. All right, so given all that, does anybody have any questions on the homework? Homework 3.
So, what would be correct circuit for the 5C?
For
5C. Because I used one input and it wasn't correct. So, how are you going to do it with two inputs?
Oh, you have an input A and you have an input B. flip-flops, one for each state. So what was the equation for state 0, for example?
For B, it goes to 0, 1.
S01? Okay. Okay, so S01 is 00 is S01B or S10A. Okay, so the state of S01 is here, and that can get ANDed with the B button. And S10 is here, and that can get ANDed with the A button. And two of those can get ORed. That goes into the B input on S00. So assuming these are all clocked together on that magically supplied external clock, this is D input, this is Q. If you happen to be in state 1, and your B button happens to be pressed, this will be a 1, this will be a 1. You'll have a 1 sitting right here at the input. And the next time the clock comes along, that 1 will get loaded into here, and you'll suddenly be in state 0, 0.
The right side is not all output. It is all output, but like the Q on the, there's a Q on the bottom, and the Q on the bottom is the inverse.
Yeah, so usually there's a Q on the top and there's a Q bar on the bottom. And Q bar is whatever the opposite of Q is. We haven't really used those in here, but
So all the outputs are going to come out of Q, unless
Yeah.
you want the input.
unless you want the inverse.
And all the inputs are going to go into D.
Right. And your clock input here. Those usually get tied together. So that they all change at the same time. So does that make sense, implementing that?
No,
Okay. Can you do the other one, do you think?
I will think about this at 4.
Okay.
I think so, yeah.
Let me know. All right, other questions
When
on
you
that?
input that into D
Mhm.
or output that, do you have to connect? Can you connect to like right before the arrow on the input of D?
Say it
All
again.
the inputs that you're inputting into, say, S00,
Mhm.
all the inputs that you're inputting in there, on the input right before D, on the arrow right there,
Mhm.
do you have to, can you connect them all to that input right there, right before the arrow?
No, probably not. So you can't connect multiple outputs together.
Yeah, that was my thing.
Right.
It's like, how do you do,
So usually, you have to go back to the equation, okay? You don't want to change just when S0 is 1 or when... If you wanted to change when either of these was true, S01 or S10, you take S01 and S10 and you put them through an OR gate. That's how you combine two or more things, if you want to combine them as an OR. Okay, if you want either of these things to be able to set this flip-flop, OR them together. Take the output of that OR, put that into your D input.
ah,
Okay, good point. Okay, if you needed both of these things to be true, you put them through an AND gate. Take the output of the AND gate and put it in there.
yeah. When I was trying to build that one that was supposed to be drawn, when I was
Mhm.
trying to do it in Logisim,
Right.
that was the whole issue of trying to figure out how to get all the inputs in on, that's why I just stuck it in wherever it could go on.
Right, right, okay.
Because otherwise, how was I to get all those inputs in there?
Right,
Yeah,
Got it.
that makes sense.
okay. All right, other homework questions? All right, homework 4 is available. It's not due until a week after the midterm. Okay, but I was actually going to give it to you on Thursday, and I forgot. But it's out there. So don't feel like you have to start it before the midterm. But if you want to, it's all about arithmetic. Okay, so binary operations, logical operations on bit strings, things that we talked about on Thursday, and that we'll continue talking about when we get to it after this review. So that's up there, and there's a Dropbox, but it's not due until a week after Thursday. When I change something on the calendar, or when I put something new in the assignments or something like that, do you get any automatic notification about it? Okay, I didn't think so. All right. I'll try to mention them. Our videos are up, okay. On the resources tab on Angel, I added a section for class videos or lecture videos. And they're up on YouTube, and they're in high def, and they're non-truncated, and they're full resolution. They're pretty.
What tags did you put on the YouTube? I just tried to look it up.
They're not public,
Oh,
so you have to know the URL to get to them.
okay.
Just because it's got people when you're first walking into class, or when you're walking out, or when you're talking, or stuff like that, and I didn't want to just kind of put that publicly available. So unless I can go through and edit them to chop out the beginning and the end and all that, I figured I'd just keep them private. So if you have the URL, which you can get to from that resources tab, it's there for each of the lectures. You can click that and go to it.
Okay.
The first few that I put up, I had to break into pieces because there was this 2 gigabyte limit, and then I found how to get past the 2 gigabyte limit on YouTube. So going forward, they're just going up there complete, 75 minutes each. Some of them are like 4 gig. So those are up there and they're available. I'll try to keep putting them up. I've got to see what the upload speed is like from the lab here.
Where you uploaded those from?
Yeah, I uploaded those from somewhere else. Okay, so those are available. All right, basic guidelines for the midterm. So it's 75 minutes that you have for it, so 2:50 to 4:05. It's going to be a really good day to show up on time, so you can start promptly at 2:50. I'll probably go by that clock, even though it seems to be slow. Everyone seems to follow it, so we'll use that clock. I'll be giving you, it'll be on printed paper, okay, and I'll ask you to work on that printed paper. It'll be 9 questions. I'll try to leave enough space for you to actually work on the pages themselves, but you might want to bring some extra paper just in case you need more. I don't think they're problems that are going to need a lot of scratch space. Definitely show all your work if you want to get partial credit, and I can easily follow what you're doing. I'll be generous with partial credit based on what you do. It'll be 9 problems, so you need to pace yourself. That's about 6 minutes per problem. Some of these will take you 30 seconds to do, okay? You can just look at them, you'll be able to write down the answers. So if you know the answers to a question, write it down neatly and quickly and move on. Okay, some of the questions will take you longer than that. Okay, I'm not trying to make your life miserable on Thursday. I'm not going to ask you to draw out large complex circuits or do sophisticated analysis of things you've never seen before. Okay, I'm basically trying to test the basic concepts that I want you to have gotten up to this point. So it should be a pretty straightforward thing. Like I say, it should be very similar to the homework problems you've done. So work quickly, work neatly, and pace yourself, and I think you'll get through it fine. If I've grossly underestimated how much time this takes and nobody can get it done, I'll adjust accordingly in my grading. So, but I think it's probably a pretty good amount of work. I recommend using a pencil and an eraser just to keep things neat, but it's up to you. The easier it is for me to follow, the more I can give you partial credit for things. So my basic synopsis of what we've learned so far in this class that you're responsible for. We talked about switches, and I don't think I'm going to test you on transistors because that's got a lot of technicalities to it, but the basic idea of switches implementing logic So if you have a switch here that's A, and you have a switch here that's B, and you have some output, when do you get current flowing from the input to the output? When both are closed, okay, that's an AND condition. Okay, this is a typical way to think of an AND circuit. Okay, what about this one? That's an OR. If A is closed, or if B is closed, or if both of them are closed, then you have a connection from the input to the output. Okay, that's what I mean by switches and logic circuits using switches. Okay, so that kind of idea. And it's important because that's where transistor switching comes from, or relay-based switching, or vacuum tubes. It's the same idea. So that's logic circuits using switches. Truth tables, you've all been dealing with truth tables every assignment now. Again, try to, when you make truth tables, try to make sure you list all the columns that you need. Don't skip steps in your head. If you're using the inverse of A to figure out some column of the truth table, make a column for the inverse of A, put it down there. Okay, it'll make it easier for you to follow what you're doing, and it'll keep you from mixing something up in your head. We talked about Boolean logic, basic identities, the fact that anything ORed with a 1 is 1. The fact that A ANDed with 0 is 0, A ANDed with 1 is A, okay, things like that. De Morgan's law for switching between ANDs and ORs. So, okay, just those two basic identities, those are De Morgan's law. And they relate ANDs and ORs based on how you do the inverses. So that's a good thing to know. Sum of products representation, so if you have a truth table and you want to write equations to implement that truth table's function, you can look at each row where you have a 1 in the output. You can write a product, okay, a set of ANDs that represents that row, and then you OR all those together for each of the rows, and it gives you this sum of products. It's not a minimal way to represent a truth table, but it does give you a representation of the truth table. So that's something you should understand. And then using K-maps to make that square, fill in the ones, fill in the don't cares, cover them with rectangles, and write equations from that to get a minimal covering, a minimal representation of a truth table. So those two things you should be comfortable doing. And then implementing truth tables with combinational circuits, so taking those Boolean equations you come up with and actually building a circuit. So if you wanted to implement this, you take A, you take B, you put them into an OR gate, and then maybe you put that into an inverter. Or maybe you just use a NOR gate. Okay, being able to take these and change them into circuits, or being able to take circuits and change them into equations and write truth tables for them. Okay, going back and forth between those. You should be comfortable with all of those different representations. So truth tables, Boolean equations, and circuit drawings. Okay, that's for combinational stuff, so no loops. And then there's sequential circuits. So latches and flip-flops, which are memory elements. Latches depend on the level of the clock. If the clock's high, one thing happens. If the clock's low, something else happens. Flip-flops are edge-triggered. Things happen when the clock raises or when the clock drops. Okay? So understanding that distinction between level-triggered and edge-triggered, and knowing how to use basic kinds of flip-flops. What's a D flip-flop? What's a JK? What's a set-reset? And so on. Timing diagrams, so being able to look at a sequential circuit like the first one in the homework assignment, and making a timing diagram from it. So where you go through each piece of your circuit and you can write down what the different levels are that that piece of the circuit hits based on what's going on elsewhere. State transition tables from a diagram or from a description. So being able to write down those tables that say if you're in this state, you know, this input, then go to this state. Okay, and maybe take some action like recognize an input or open up a lock or something like that. basically being able to go between those transition tables to diagrams where you have the circles with the arrows that show you which state you're in and how you move from one state to another, and descriptions of state machines. What is it doing in terms of, we're trying to match a pattern DOG. So going back and forth between those different representations of states. And then you should be familiar with implementation of a state machine from a diagram or from a transition table. Okay, that's like problem 5 on the homework. I'm not going to ask you to implement a state machine with flip-flops and combinational logic for the exam. Okay, I have other ways I can test your understanding of their concept. So I'm not going to have you actually draw out a circuit containing all the elements of a state machine for the midterm. But you should be comfortable with the ideas involved in that. Okay, and if I give you a picture of a circuit diagram of a state machine, you should understand what's going on. You should be able to look at the input to a flip-flop and see that it's coming from this OR gate and figure out what the transition table might look like from that. Okay. And that's pretty much it. I mean, that's a lot of stuff, but that's pretty much what we've been covering up through the point where we started talking about arithmetic. And if you're good on those, you're good to go on the midterm. So what are your questions at this point?
So which one's latch again? I forgot which one's that.
Latch is usually level triggered.
What is the mark or the diagram of it?
Yeah. Okay, so you have a clock input, you have a D input. Okay, if your clock is 1, your output is just whatever your D input is. Okay, it opens up the latch basically. Whatever comes in immediately appears on the output. If your clock is 0, then your output is just, let's say, Qn minus 1. It's whatever the previous value of your output was.
Like that first one in the homework column then, right?
Yeah, sort of.
Isn't it? Because that was essentially the truth table.
Yeah.
No,
You-
it was just when they were both 0, that was when the output was.
That was when it's flat.
Not 0 and 1.
Right.
Yeah.
Yeah, that circuit in the homework is basically a latch because if your input was 0, 1, then it was set to a 0. And if it was 1, 0, it was set to a 1. And I mean, we didn't really have a clock in there, but we thought of it as that having a clock would probably be more like a latch. But so this is level trigger. Okay, if your clock is 1, you can load values into this device. If your clock is 0, it's locked. Okay, the output is fixed. The flip-flop actually, any time that the clock is 0, your output Q is exactly whatever the previous output was. If you look at it and your clock is 1, your output is also stable. Simply having the clock at 1 doesn't change the output value. If the clock's 1 and I change the D input from 0 to 1, nothing happens. Okay? It's when the clock raises from 0 to 1 that the D input affects the output. And if the clock raises from 0 to 1 and the D input is a 1, then the output's a 1. These are the only cases where the output changes, is when this is actually changing from 0 to 1. Okay, so that's an edge trigger.
So it doesn't do anything even if the clock goes from 1 to 0?
In this case, it's a positive edge trigger.
Okay.
Okay, so when this goes from 1 to 0, it's unchanged. It's only on the rising edge. And negatively edge triggered, obviously, it's these cases where the output would change. Okay. The words flip-flop and latch are probably not rigorously defined. What's rigorously defined are the terms level triggered versus edge triggered. Okay, if someone says level triggered, they're positively talking about this case. If they say edge triggered, they're positively talking about that case.
And we have different kinds of flashes, like T-latch, GK, so the same.
Yeah, so, can I erase this?
Hang on.
Okay.
Okay.
And does it have the same inputs, so D, lock, and Q minus, and minus Q?
Okay, so T-latch is just a data latch. It has one input data, and when the clock's high, the data gets loaded into the output. When it's low, it's closed. An SR latch has two inputs, one for setting it and one for resetting it, and an output Q. As soon as S is 1 and R is 0, the output is 1. Okay, if you hit the set line with 1 and the reset is 0, your output goes to a 1. If you have set at 0 and you hit the reset line, the output gets cleared. Okay, reset to 0. If set and reset are both 0, then it's locked, and the output is whatever the output was a moment ago. Okay, that value is latched in. And we don't really talk about state where S and R are 1. That's sort of an illegal state.
What'd you call that?
That's an SR, SR latch.
Isn't that basically what our first one was? That not what I was thinking?
No, this 1-1 was, we cared about 1-1.
Yeah, I mean, it basically acted like that. One of the inputs would set the output, and one of them would clear the output. But it had some weird stuff in it. And it was stable when both inputs were 0. Yeah, it was kind of weird. I think they were the only two latches that we actually talked about, the only two things that are actually level triggered. Edge triggered flip-flops. Here's the data. Okay, and I just drew the truth table for that over here and erased it. But when the clock goes from, say, 0 to 1, D gets loaded into Q. You can have edge-triggered SR flip-flop. And so if S and R are 0, well, it doesn't matter what your clock is, Q is going to be stable. If your reset line is set to a 1 and your clock jumps from 0 to 1, then Q becomes 0. If your set line is 1 and your clock jumps from 0 to 1, then your output is 1. 1, 1, we'll just say that's illegal. And if your clock is not changing, if your clock is either 0 or 1, it doesn't matter what S and R are, your output is still just whatever previous value of the output was. Okay, it's locked. So the only time that the output changes is these two cases. Okay, you turn on the set line, you clear the reset line, you pulse the clock, that'll set it. Or you turn off set, you turn on reset, you pulse the clock, and that'll reset it and clear it. Okay, and then there was JK. JK was basically like a set reset flip-flop, where J is the set, the K is the reset, but it has this extra feature. If J and K are both 1, then every time that you pulse the clock, the output toggles. It changes between 0 and 1. So this is no longer an illegal state. The value here would be the complement of Q in minus 1. And then for simplicity, we sometimes talk about a T flip-flop. Which is just a JK flip-flop where J and K are both 1. So it's just a JK flip-flop that only operates in this state. So that every time you pulse the clock, the output toggles. Okay, it's just a toggle flip-flop.
I'm having a little trouble with the timing diagram.
Okay. Okay, 2 inverters and an exclusive OR gauge. And for this case, let's say there's a 1 nanosecond. Works, whether there's propagation delay being considered or not. So I want you to show me what the timing diagram for X looks like based on this circuit when A acts like this, okay? It's kind of like drawing truth tables, but it's a whole bunch of truth tables, okay? It's a truth table where A is 0 for all of these values, and then A is 1, and then A is 0. And in sequential circuits like this, the truth table only shows you kind of a static picture, a snapshot. If A is 0 and B is 0, what is X equal to? Okay, sequential circuits, you need to know the history of A and B. Okay, that's the whole idea of having state. So a timing diagram shows you the history of A. A was 0 for all this time, and now it's 1, and now it's 0. Okay, And simply knowing that the value is 1 right now may not tell you the complete picture. So usually for sequential circuits, we like to do timing diagrams. This is a combinational circuit, but it's the same principle. So when you're trying to write a truth table for something, you want to identify all the points in your circuit that you need to know the value of. Okay, if you want to know the value of x, you need to know the value here and here. Okay, well we know the value here is just a, but we don't know what the value here is. So let's call this point A1.
Well, those are 2 NOT gates, right?
Yeah.
Well, it's going to be the same as A.
Well, it would, except that we're considering propagation delay here. Okay, so we want to see how this acts in time. So A1, to know the value of that, we need to know the value that goes into this NOT gate, which we can call A2, and we need to know the value going into this NOT gate, which is just A. Okay, so just like the truth table, we're going to find out what each of these values are sequentially. So A2 we can determine directly from A. That's the only one we can determine directly. We can't determine A1 until we know this. We can't determine X until we know A1. So we have to start with A2. And it's the inverse of A, so it starts off high. And at this point, A goes high, so A2 is going to drop, but it's going to take a nanosecond. So we're going to come out 1 nanosecond more, and then we're going to drop. And at this point, A is going to go to 0. And so a nanosecond later, A2 is going to go high. Okay, and what does A1 do?
Here's A2 with that. Yeah, nanosecond delay.
Right, so it's the opposite of A2. 1 nanosecond later, where it is. 1 nanosecond later, it drops. Okay, now we know the 2 inputs to the XOR gate are A and A1, and so we can write X. So it starts off at what?
0.
0 XOR with 0 is 0. At this point,
1,
A is
0.
1, and this is 0. So the XOR is going to go high, but it's going to take a nanosecond. And at this point,
Got 2 1s, so it'll pop back down to 0.
it'll pop down to 0 after a nanosecond. Okay, so you've got 1 and 1, and at this point, A drops to 0. She has a 0 and a 1. So the XOR should hop up again, but it's going to take a nanosecond. Bless you. And then when you get to this point, you're going to have a 0 and a 0. So your XOR is 0 again, but that takes a nanosecond. So it drops down. Okay, and there's your output X, and now you can see that there's a glitch. That even though the output should always be 0, it has this little bump that it creates. Okay, that's an example of a timing diagram.
Okay.
Now if it was a sequential circuit and it had outputs going back to inputs, it's exactly the same procedure. Okay, you just put down the different pieces of the circuit that you need to know, and you work through them and write them out one by one.
So, after doing that, what would be considered the glitch in that example?
These things here.
So the inside parts?
Yeah, because if you write the truth table, X is just supposed to be 0. Right, because A XOR with A is always 0. But it's not. It's supposed to be 0, but it takes on the wrong value for 2 nanoseconds in between. Okay, let me change the input. But you know what's cool about this? We took the input to the circuit and we went up and down. The output went up, down, up, down. Okay, it's a frequency doubler. You can take a pot and you can get 2 pulses out for every pulse you put in, which is really useful sometimes. It makes things go faster than when they're coming in. know how to make a frequency divider? Toggle flip-flop. Right, if this is positive edge triggered, every time that your clock goes from 0 to 1, your output toggles. So it toggles here, here, and here. So it toggles to a 1, toggles to a 0, toggles to a 1. Okay, that's a frequency divider. You go up, down, and this goes up and down. Okay, so it lowers the frequency. If you really need to, you can double the frequency, that kind of circuit. That's not a really great circuit to work with because it depends on the propagation delay, and it can be a little hard to control, but you can actually use it to bump up frequencies in some cases. All right, what else?
Possibly go over a few K-maps.
Sure. Colored pens are great for K-maps. That's not too bad. Start. Okay, 4 variables. Two variables on each axis. All right. And what order do we put the zeros and ones in?
0, 0, 0, 1, 1, 1, 1, 0.
Right. Okay, that's a gray code. Only one bit is changing from one to the next to the next. All right, start in the back, go around the room. Give me a 1, a 0, or a don't care.
0.
1.
Don't care.
1.
Just pick a 0, 1, or don't care.
0.
1.
Don't care.
0.
7.
1,
Don't care.
1.
0.
1,
Don't care.
0.
All right. There's a good chance when I can ask you a question, you can answer don't care. All right, so here's a essentially random K-map for a truth table. So you're comfortable with how you would have created this from the truth table? You just go through and for 0, 0, 0, 0, you put in the value in the truth table and so on. So usually the tricky part is covering it. So you want to cover your ones, you're allowed to cover your don't cares. You can't cover your zeros. And you want to use as large your rectangles as possible, and you're allowed to do the asteroids model where you wrap around on the ends or you wrap around the corners. So I guess the way I usually do this, I just start looking to see if I can just eyeball it and find large groups of ones or dashes.
You can have 4 or 5 boxes depending on how you do it. You'll have a 2 by 2 in the center.
Okay, like this.
Yeah. one more, another 2x2, move one box up from that,
right?
yeah. You'll have a 1x2 on the very last row wrapped around top and bottom.
Mhm.
You'll have a 2x2 on the bottom left corner,
Right.
and you'll have a 1x4 in the 01 row.
Oh, you're gonna do
Well,
that.
it's already
Covered.
covered.
No.
Yeah, you already covered, yeah.
So I got those. Those.
You want to-
That.
More boxes.
So that would cover all of your ones. Alright, is there any way we could do better?
Nope.
I think so.
The only most efficient one you could get out of it.
Turn everything to one. That's the best answer, yes.
Instead of that 1 2x2, you would do that whole row, but that doesn't change a lot.
Yeah, you can come down like this, and cover those, but that's still gonna be, a 1x4, which I think will be the same as a 2x2. So I think that's probably the best we're gonna cover. Like I say, it's not unique, there's different ways you can do it, but in terms of how many AND gates, how many OR gates, how big they are, the size of the rectangles is all that matters. And I think that's a minimal covering. So the first part is going from your truth table to filling in the 1 zeros and don't cares. The second part is covering it with smaller rectangles. And the third part is writing the equations that correspond to that. So if we pick out this red rectangle on the top,
Not WZ.
Yeah.
right? So W is 0 in all these cases. So that means W bar has to be true.
And
X can be 0 or 1, so it doesn't matter. Y can be 0 or 1, so it doesn't matter. And Z has to be 1. So W bar Z expresses these 4 entries. All right, what about the purple?
XC.
Right, W doesn't matter, X has to be 1. Y can be 0 or 1, Z has to be 1. And then the blue,
W not Z.
W not Y.
Oh, yeah, sorry, yeah, W not Y.
right, W is 1, X can be 0 or 1, Y has got to be 0, and Z can be 0 or 1. And in the green case,
W, Y, not Z.
Actually, wait, no.
There should be 3 terms.
Yeah, W, Y,
Yeah.
not Z.
Oh.
It'll be Y not Z not X.
right,
Oh,
so W can be 0 or 1, X has got to be 0
I
though.
screwed up.
Okay.
Oh no.
Gotta
And
be
then
Y.
World's
here,
gonna end.
10 points.
And W not Z.
Set, reset.
And we can set our value to 1 in any of these cases, so you OR those all together. And that's the Boolean expression that corresponds to your original truth table.
That'd be cool if all 9 questions were
For some people,
For some people, or I could do like an 8-variable K-map and make it work in hyperspace.
Awesome. I would see that.
you can, it's called a Katy tree.
Oh, no.
I'm not going to ask you to do like hundreds of K-maps. Okay, you may see a K-map on there, but it's not going to be like your homework problem where you have to do 7 of them.
100
Like I
variable
said, I'm just
K-map.
trying to test the concepts, okay? I'm not trying to see how fast you can work, or can you learn new material under pressure or something.
Throw in a random question if you think it's going to be difficult, but it's just 2 plus 2.
Yeah. Or
Plug
define
in
the
zero.
universe and give 3 examples.
Plug in 0.
The answer's 42.
42.
said we're gonna have one sheet of notes.
Yeah, okay, thank you. Yeah, you can bring in 1 page of notes if you like. Double-sided, you can write it by hand, you can print it out on a computer. You can take the whole book and make it into microfilm, but I recommend it.
I've done something similar to that, actually.
Yeah, I've
Oh
done
my
that.
gosh.
They're good references down the road if you want to sell your textbook. No, but yeah, bring in a sheet. Like I say, the list of things that we've learned is not that long. The concepts behind them is a different matter. But I think you've all got those concepts down at this point. So if you want something to jog your memory, that's fine. Oh, and when you draw circuit diagrams, let me ask you, if you make an OR gate, put a plus in the middle, just so that I positively know it's an OR gate. Okay, this little curved symbol in the back tells you it's an OR gate, and this is an AND. But if you're rushed and you're writing in pen and sometimes it gets sloppy, it can be a little hard to tell what the difference is. So if you put a plus in there for an OR and a dot for an AND, that makes it really clear. You got a question first?
Yeah, do we have to know the circuitry and the flip-flops and the latches?
No, you don't have to memorize those.
Okay.
You may see them, and it may ask you to do some analysis of them, but no, you don't have to memorize how to make a flip-flop or something like that. Yeah.
Will you have to actually create a lot of circuits on the test, or?
I know a lot.
More than half?
No.
Okay.
Most of your circuit design is going to be going from, say, Boolean equations to putting down gates and putting wires to connect them together. Okay. Again, just to make sure you understand the concepts of how these gates go together, the idea of taking two things and ORing them to combine them, if you want to OR and stuff like that. Anything else? All right, I'll post this lecture this afternoon. I'll try to post the video this afternoon or tomorrow morning today. Shoot me an email if you have some concerns or questions about your homework. And I will see you on Thursday at 2:50.
Awesome.
Double line and circle around.
They're on a different
Yeah,
planet.
listening to you all is super
Yeah.
freaking out about taking that.
This is an order.
Well, you just want to make sure you've taken your calculus first. Or at least Calc 2, right? Or no, Calc 1 at least.
I think so. Yeah, it looks like it's that one problem.
It's an XOR, it acts like a
Going for
regular
the
OR,
board,
except on both
it
your
looks like substitution. Figure out.
Well, the problem with the
It says
substitution is
either
that you
A
figure out
or B,
which equation
not both.
to use first. And then you start subbing things in. Then you say, okay, well, I don't have a known type, so I have to use your equation to sub in for T. Then do this, and so it's like, yeah, so it's not quite as simplistic as just substitution. You don't know what it is.
Well, right, I mean, it looks complicated, but it doesn't look, at least yet, it was involving holes.
So you're going to have a change.
Oh, well, there's,
The scoping, that means I need to.
Yeah.
This is good. Right?
Yeah, because we take that extra, that's what we already know, that's true. That is what we do. So, I hope, that's what we take that shit? CS 122.
From 0 to 1.
Oh, at least that's on our thing, it's on our.
X for where 0 and 1 is, and it goes to 1.
Right.
So then I have 1 second delay, and then I go back to 1.
No, she's not coming this weekend, I gotta go there next weekend. Oh, okay, her birthday, that's why. Oh, yeah.
What is this? Why here? There's nothing that happens until
She wants to
here.
go to Jake's. She wants to go to Jake's. Jake's.
Oh,
Oh my God. Why'd you over there?
I don't think it's not exactly right.
Well, that's why she wants us to bring you on.
And you, okay. Think what happened
Dude, that's crazy.
is you made this pretty small compared to this 1 nanosecond delay.
So should we make this smaller?
Yeah, exactly. Or made that first
We
one.
were watching what you doing. I was like, we need to play. I had at one time,
Right.
my 21st.
Okay, this is going here. Looking up here,
I was like, that's weird. So, is this something you're telling me? When you're drunk, you need to do that?
Okay, and this one has to move also. This changes 1 nanosecond. Just
Fucking guys.
What is it, right?
Nah. Wait, Gabby. Dude,
so then
pretty fingers.
we're looking.
I'm gonna bring around my fingers and meditate before I go to play.
And we're gonna wait till we get here.
Actually, when you get right there, you're gonna get on your both one.
So it's either one of them does something,
Yeah.
not just this one, it's when either one does something.
Right.
Okay. So now, this one is going to 1, and this one's at 1, so it's gonna go to 0.
Right,
But there's gonna be a 1-second delay.
exactly.
Okay. So
Okay.
when either one does something,
Mhm.
then it's gonna do something.
Right.
Wait.
Okay. All right.
Is that yours?
And if you continue that diagram, you want to change your propagation delays on
This
the
doesn't look
other.
the same as this class though. This is 453, so that wouldn't be as high.
Okay, so
This is really new.
CS 453?
Yeah.
I know we have like 2 CS names in our little thing.
Well, one was, unless there's a third CS program.